Great pleasure to welcome in the Al-Khwarizmi seminar of applied mathematics Bernhard Gittenberger, which is in fact just next to me in some seminar room here in Wien at the Technical Universität of Wien. So Bernhard is a close colleague for many years, and so in fact he got his PhD thesis in 95 under the direction of Michel Mota. So it was on the height and the width of trees, of random trees for sure, and links with Brownian motion theory and so on. Since he did more than, I don't know, 60 articles on different topics related to trees, permutation, graphs, lattice paths, and more recently, after some collaboration with different countries like Poland on lambda terms, or France, it was more lattice path and so on. He had some collaboration with some people in Taiwan, Michel Fuchs, which is in fact also a former member of TU Wien, and with some nice links with bioinformatics, and leading to some interesting limit laws that he will soon present. So Bernhard, the floor is yours.
So thank you very much for the kind introduction. Maybe I'll switch on the and thank you very much, Rafik, for the invitation to present this work here within this seminar or webinar. And I talk about an Airy limit law for the balance of labeled and unlabeled gold trees, a structure in bioinformatics or biomathematics, and which is joint work with Michael Fuchs from National Chengchi University in Taiwan. And so I have to get access to this. Okay. Well, a very classical model in evolution theory is phylogenetic trees. So you start with a set X of, let's say, n taxa. So these are species that we can see nowadays. And the question is, how did these species evolve? And so biologists are interested in finding proper models, and in particular, how in finding the size of the search space for these proper models. And so this gives rise to a phylogenetic tree, which is a rooted, yeah, I know, but this doesn't, this is just for you, okay. A phylogenetic tree, which is a rooted complete binary tree with the leaves labeled with the elements of this set X. So this is a classical model for evolution, but it's not enough, as new types of evolution have been discovered. And for instance, in evolution of bacteria, some other things happen. It's not only branching, but sometimes so-called reticulate events occur, where two different species may unify to a new one. And so the model is not a proper model for this. And so was there a question? Because my microphone is off. Okay. Okay. So other models are needed. And therefore, biologists came up with phylogenetic networks. And the rooted phylogenetic network for us is a rooted directed acyclic graph, such that certain properties are fulfilled. First, all edges are directed away from the root, so directed graph. Then the root has either no child, then we have a so-called trivial network, or it has two children. So all the other vertices belong to one of the three types, namely they may be leaves. That means they have one parent and no children, and they are labeled with one of the taxa from the set X. They may be tree nodes, meaning one parent and two children, or they may be reticulation nodes, meaning two parents and one child. So basically we have these three types of vertices. Here the leaves are labeled, and here are the tree nodes, and here are the reticulation nodes. And the size of a network here is the number of labels, so the number of elements in the set of taxa X. Special classes are, of course, phylogenetic trees themselves, because to just require that there are no reticulation nodes, then you have a phylogenetic tree. Or so-called tree-child networks, where a node, if it has children, then not all of them are reticulation nodes. This is a very common model in biomathematics. Then normal means there are no shortcuts. And one component for simplex tree-child networks are networks where the children of reticulation nodes must be leaves. So here you see a tree-child network that is simplex. So all the children of the two reticulation nodes are leaves. This is also a normal one, whereas this is not normal and neither tree-child, because here you have a shortcut. Here you can go on a path of size 2, and shortcut means a direct connection that realizes an already existing link, which is not direct. And here you have both properties. And a gold tree, it's another kind of tree-child network. Namely, that's a tree-child network where all biconnected components that biologists call blobs contain only one reticulation node. So you see, this is an example for a gold tree. There is the first goal, which is this biconnected component having one reticulation vertex here. And this is the second blob, or the second goal, like they are called in this context, also with one reticulation vertex here. Whereas this network here is not a gold tree as the biconnected component. There is only one of them, which is just a network without the leaves, but it has two reticulation vertices here and here.
And it could cross the reticulations, they could cross.
I don't understand what you mean exactly with crossing here.
The reticulations, they could cross another reticulation so that it's not planar.
No, in a tree-child network, this cannot happen.
Okay.
Yeah, because everything is kind of, well, on a non-planar could happen, but not in gold trees. So in gold trees, everything of these kind of special cases may happen. It can be normal or simplex or none of it or both. Interesting. None of this is normally not interested. Normally, you require normality or simplex or both properties. So you see here a gold tree, which is not simplex because the reticulation node, which is red, has not a leaf as its child. This is not normal because there is a direct link of two vertices that are already linked here. This is also not normal. This is not normal and neither tree-child, neither simplex. This is normal, but not normal, but simplex. And this is both. So we are interested in the balance of such structures, and the balance is, there was a suggestion by Sekin for the balance of phylogenetic trees, and we kind of adapted this to phylogenetic networks or to gold trees, and therefore we define for a tree-child network N, or a gold tree, the longer height of X is denoted by H plus, and this is the length of the longest path from the root to X. And likewise, if we replace longest here by shortest, then we call this the shorter height. Here is a tree where the longer height is depicted in this red path. You see the longer height of 8 is 1, 2, 3, 4, 5, and 6, whereas the shorter height is 5, because then you would not take this path, but this path instead, and you would get 5 edges to the root. And the second index is now the sum of all this. So we denote by S plus the second index defined as the sum of all longer heights here in red. the longer heights of the vertices. The black numbers are the labels of the vertices. The red numbers are the longer heights of the vertices, and the blue numbers are the shorter heights of the vertices. And this gives rise to two different second indices, namely S plus, where you sum up the red numbers here, and S minus, where you sum up the blue numbers here. And we are interested in this quantity for these three. Some historical remarks. So phylogenetic trees are they are simply generated trees.
Is a question?
Leaf-labeled binary trees. And there are a lot of results dating back to René Sekeres, then later Knuth, Rice, De Bruyn, Knuth, and Rice for plain trees. Meyer-Moon studied the height of random nodes in so-called simply generated trees. Kolchin gave a probabilistic approach, and well, the most important theorem for laying the ground for this is the theorem by Flageolet-Litzko on the average height of a random binary tree with n leaves, which is 2 times root of pi n. And as a consequence, we get the average height of a random phylogenetic tree is of the same order and even the same leading constant.
Please, I have a question, please.
Yes.
In the previous slide, where you have defined S plus n, can you more, can you?
Je peux mettre mon son, Bernard, si tu veux. Rafik, can you repeat the question?
In the previous slide, where we have the definition of S plus n. S plus n. 4 plus 4 plus 4. What means S plus n? Is the sum of depths of leaves or what? S power plus of n.
Yes, S plus of n is the sum of all the longer heights. So that's the depth of the leaves, but where we choose always the longest path to the root. And S minus of n is you choose always the shortest path to the root. So for instance, for the leaves 8 and 9, okay, you have to choose here not that way, but you have to go that way. Then the height of the leaf 8 and 9 is 6. Whereas if you go that way, then the height is 5. And for S minus, you always go the shorter way. And for S plus, you always go the longer way. Okay. And you sum up all the leaf heights.
Okay, so S plus n is the sum of longest paths from the leaves to the root. And yes, S minus is for the shortest paths.
Exactly.
Okay, thank you.
So, and the second index of phylogenetic trees is then closely related to the path length, which is the sum of all node heights in trees. Yeah, but now we have not exactly a tree-like structures, but something that is a bit more complicated. And for trees, there's a lot of things known about the path length. For instance, Luchard, Tarkac tackled the distribution and moment asymptotics. Fuchs and Huang and also Neininger did this for binary search trees, which is known also as Yule trees. Generalizations of this have been tackled, and there is also the second index for a random phylogenetic tree was treated recently, and even there is an exact formula for that.
Hello, Cyril, you hear me?
And also an asymptotic, of course, gold trees. Their bounds were given in a recent paper by Chang. Okay, I don't know if I should go into these combinatorial structure things. I just will go through this quickly because I think it's maybe well known to the audience here. I just repeat what we need for going ahead in this in our setting. So we have a combinatorial structure is a set of combinatorial objects. So this is just an abstract set where each object comes with a size and is composed of distinguishable atoms, where the atoms are distinguished by their labels. So they carry labels from 1 2, 3, and so on, up to the size of the structure, which is the number of atoms. And we call such a thing a labeled combinatorial structure. And in addition, we say AN is the set of all objects in this combinatorial structure that have size n. We require that for each n, this set is finite. Then, of course, we can think of counting. So that means A sub n is just the size of those sets, AN, and the sequence formed by these A sub n's is called the counting sequence of the combinatorial structure A. And this is what we are interested in. And we do this with the use of exponential generating functions. So that means we encode the counting sequence in terms of a power series where we put AN as the coefficient of z to the n over n factorial. So this is the exponential generating function associated with A. And what is the advantage of this encoding is the symbolic method developed by Flageolet and numerous co-authors. And I will just give a very brief list of some results there that we will need for the further analysis. Namely, we can sum up two combinatorial structures by just taking the union of them, and we require that this is a disjoint union, and by taking the size of an object of the union by taking the sizes of the given sets already, then the generating functions the generating function of the new structure is just the sum of the generating functions of the two structures that build the new structures. The combinatorial product, similarly, you take the Cartesian product of two structures and take that the size is just the sum of these two. But of course, we have to be careful because then we have duplications in the labels. So we have to relabel in an order-preserving way. And we have a lot of choices to do that. For the exponential generating function, that means in the end that the generating function of C is then the product of the generating functions of A and B. And then we also need the symmetric case where if you kind of do not distinguish between xy and yx, so then we write it in this way, and the generating function of that is just you have to divide by 2. Then you can build a little bit more complicated structures from this by, for instance, sequences of positive length. So you take a combinatorial structure and then you build a sequence by taking A and the union of A times A and A times A times A and so on. And now you can directly translate what we already know, that A is has generating function A of Z, the Cartesian product has A of Z squared and so on, and you get a sum, a geometric sum, and under some restrictions, namely that there is no object of size 0 in A, this can be summed up formally and gives rise to this formula here. C of Z is this expression then. And there are many more constructions treatable in this framework, and also the whole thing can be done for structures without labels by going to ordinary generating functions without the normalization of n factorial instead. Now let us apply this symbolic method to gold trees. For instance, we can specify a gold tree in the following way. A gold tree, let's call it R, the set of gold trees, is either a trivial gold tree, which is just a single vertex, or it is in the single vertex, it's an end node, so it has a label. It counts to the size, whereas the inner vertices do not count to the size. So therefore, I distinguish them with the two symbols here. Or it can be, well, we can have an inner vertex as root with two successors, and then we have a symmetry, because we may swap here. The same for, or we have the root lies in the goal. So that means we have we may have, if we have not necessarily normality, we may have a large part to the reticulation, a large path to the reticulation vertex, and a shortcut. So then we have this kind of structure, or we may have a goal which is a bit more complex. But then, of course, if the two paths are of the same length, this is symmetric, so we can just swap them. And now, using the dictionary, we get a symbolic equation. So R is either this set here or the union of this structure here, which is a root times R times R. Yeah, symmetric product here. Or it is such a thing here. Then we have, this is R. This is a sequence of R's. So we can write it like this. And of course, there must be this reticulation vertex. So that means the sequence has at least one. Here, it has at least one element. And the reticulation has at least one here, because double edges are not allowed here. Or it is the root goal is a bit more complex. Then we have a structure like this. We have an R for the reticulation, and we have two non-trivial, so two sequences of at least one R that build these two substructures. And well, we can translate this directly into generating functions and get a functional equation for the generating function of these gold trees, which is this equation here. And well, this was already studied by Bouvel, Gambet, and Mansouri, and they obtained the explicit solution. So this is a cubic equation, but since we are searching for a power series with positive coefficients, that means the solution must be monotonically increasing on the positive real line and convex. And of the three solutions of this cubic equation, only one of them satisfies these two properties, namely this one. So we have an explicit solution for this generating function. Now, we can do even more if we take into account the second index at the same time. So let R and K be the number of gold trees with n leaves and second index equal to K. And write this generating function. Now we have a generating function in two variables, which is exponential in Z and ordinary in X. And now we do this more or less the same. Let's, on the next slide, first of all, what does this function help us? Well, if we have a random network N with n leaves, and we are searching for the average second index, then the average second index is just this number here, which is built from these coefficients, and which is just the coefficient of Z to the N of the partial derivative with respect to X of this function here, where you plug in Z and 1. So all we need to find is this function, and then we have to find the coefficients of this function. And to find this function, we do basically the same as before, where we got the function R of Z. Namely, we use the same specification we can use by additivity. So this specification, and we got this functional equation. Now I write it a little bit more explicit. You see that, for instance, this product, okay, we keep it. But if we have here two equally long paths, then this corresponds to some subterm of this last term, which is exactly this one. If we are in this setting, then we have actually here a path of length 0. So this is corresponding to L equals 0 in that case, and a path of larger length here. So we are in a non-symmetric case. So this is the L equals 0 term of this here. Or for larger L, we have more complex but not symmetric terms, which correspond to the remaining terms of this sum. And now we can look what happens to the second index. The second index is the sum of the leaf heights. So that means if we look at some R here, then what happens to the leaf heights? They are increased by 1, 2, and so on. In this case, r plus 1. The leaf heights here are increased by k plus 2, and so on. So for instance, for this, the leaf heights are increased by 3. So that means if I know how many leaves are there, but this is exactly the size, which is encoded in the variable z, and I know that all leaves contribute 3 more to my leaf height, then I have to replace just z by z times x to the 3. And so we do this for all these subterms appearing here, and we get this functional equation here. Okay, that looks more complicated, but still we can do. We are interested in S, which is the derivative of this with respect to z to x. So let's derive this with respect to x and set x equal to 1. Then we know that, well, what will appear? We will have some partial derivatives in z.
Il y a peut-être une question, Bernard. Wissem, tu as une question?
Could you please come back to the previous slide?
Yes. Alors, on entend mal ici. Tu peux répéter? J'ai changé l'ordi pour le son. Can you repeat the question?
No, I didn't ask yet my question. In the second line, in the first equation, the second equation, sorry.
Yes.
There's probably a gap. Everything is in Z. We don't see K, I, L, etc.
In the second line, this is the univariate setting. So there is no X yet.
There is only Z in the product and the sums. The index do not appear at all.
It's the bound for the product, the L and L.
Yes. Did you hear? Donc, dans le produit, les produits ils vont jusqu'à K et ils vont jusqu'à L. Donc, ils apparaissent en exposant dans le produit.
Donc, c'est RZ à la puissance K, c'est ça?
Oui, voilà.
RZ to the power K. The product from 1 to K of RZ.
Yeah. This is Z. This is, in fact, it's what you get here is R of Z. This is just, I mean, a more complicated writing for this, right? So this is just the power R of Z to the power K plus L plus 1.
Okay.
But I wrote it on purpose because each R here corresponds to one of those R's in the picture here. And now I replace, let's say, the R which is on position I by such a term here. So in this product here, it's this one. The ith term is on position I here. So that means the leaf heights are increased by I plus 1. So that's why I replace this Z here by Z and X to the power I plus 1, and I need the second variable X. So here all the R's are the same. So this is on purpose a more complicated writing to see that here each R is replaced by a different term in that product here.
Yes, to pave the way to the most complicated setting.
Yes.
Okay.
Okay. Now we have this functional equation, and we derive with respect to x. So that means we get partial derivatives with respect to z evaluated at z and 1. But this is just r prime of z, where from the univariate function r of z with the derivative, and we get the partial derivative with respect to x at z and 1. But this is our function s of z. So if we do the derivation of this, then everything will become quite nice. So we get the functional equation of this form, s of z on the right, on the left-hand side, and then we just sort with respect to the terms that bring us in r prime, and the terms that bring us a z, an s of z on the right-hand side. And in fact, it turns out so these f and g, these are explicit functions. So we can solve with respect to z and get this quotient here, where f and g are just rational functions, which are quite explicit. All right, so now we have our function s of z in a certain form. And the next we have to do is to find the coefficients. And to find the coefficients, we use singularity analysis, which is based on the following definition and the following transfer theorem. The definition is a function is called delta analytic if there is some domain delta which looks like this indented disk, which is slightly larger than the disk of convergence. So here at rho, we have a singularity on the circle of convergence, and we can have an analytic continuation to some domain that has this shape. So this is there exists some range here that we can slightly go beyond the disk of convergence. And if we have a delta analytic function that behaves near the singularity like some nice function, like a power of 1 minus z divided by rho, then that means that the coefficients of that functions are asymptotically equal to this expression. So where gamma is the ordinary gamma function and rho is this singularity here. And we will make use of this first for the univariate function. This was a very explicit function, and we see that for z equals 1 over 8, there is a singularity. And in fact, if you approach this value, then the function r of z behaves like this. So there is this singular part where we have a root. And so that means we can directly use the transfer theorem with rho equals 1 over 8, and we get this asymptotic formula for the coefficients of r of z. That gives you the number of gold trees with n leaves. So this can be simplified in this way. And now we do the same with S, because S depends on this function in a very, let's say, controllable way. It's just you plug this into some rational functions, and then you have the quotient of this. So this is basically a rational function of R and its derivative. So we can just calculate how this behaves if z approaches 1 over 8, and it turns out it's just this expression here. And a transfer theorem gives directly that the nth coefficient is then asymptotically equal to 8 to the n times some constant. And now the expectation of S plus, which we were interested in, is just a quotient, z to the n s, because S encodes the expectation, the average second index, divided, well, normalized by the number of gold trees, which is the coefficient of R, the nth coefficient of R, and just you do just here the quotient and get some constant, explicit constant times n to the 3/2 as average second index of a asymptotic average second index of a network with n leaves. Well, you can do some variations. For instance, simplex gold trees. Here, the only difference is in the specification is that we do not allow an R structure here, but this must be a leaf because this is a reticulation vertex, and here as well. This is the only difference. So that means we get the same here, where we replace the R values here by the single vertex, and in the functional equation, one factor R is replaced by Z. And now we can do the same game here, and we get one solution that is a power series with positive coefficients, which is this one. And from this singularity analysis gives you that there is one singularity at the value rho, 3 minus 2 times root of 2. And R is delta analytic near rho, and behaves locally like this, a constant times another constant times a root of 1 minus z divided by the singularity. So the transfer theorem applies directly, and we get the asymptotic number of simplex gold trees with n leaves to be exactly this value here. Likewise, we can do this for the multivariate setting, where we go back to this functional equation, and now we do again this replacement of the R's, of all these R factors here by the proper R of Z times X to the proper power here. and x in the second variable, and get a functional equation for the bivariate generating function, where x is now keeping track of the second index. And then we can do the same game again. Start with this functional equation, do a derivative with respect to x, and put z equals, with respect to x, and put x equals to 1. And then we again have s of z is a kind of a rational function in R and R prime, and has an explicit behavior, which is this part here. And so again, we get a formula for the second index for the asymptotic expected second index of simplex networks. Okay, maybe I'm running out of time, so that means I may rush of this. Normal trees, there is this third case where we have the shortcut is forbidden. So we are left with the three cases. So that means we lose one of those terms. And similarly, we can do this. In this case, it's a fourth order equation. And the solutions are not so nice that they can be easily handled with Maple. But anyway, we can do this numerically still. And also in unlabeled settings, you have to appeal to the ordinary generating functions and use some analogous dictionary, which is a bit more complicated, but still doable. So in this case, everything can be done, and all the characteristic parameters are, of course, then only available in a numerical way. We don't have such explicit constant as in the previous cases. All right. Now, let me briefly refer to some other connections, like the path length of simple generated trees is known to be related to the Brownian excursion area and has an Airy limit law. And this parameter is also related somehow to the path length. And indeed, Stufler presented that there is a weak limit to the Brownian excursion area for the second index of Walsh trees. But the analytic approach that I presented here gives more. It gives even a moment convergence, and also the weak limit theorem we can have from this. And this is the thing of the remaining slides. So again, go back to the functional equation as we had it for the bivariate function. And now you see that there is kind of a certain pattern behind it. If you write phi is kind of a structural function. So this is a function where each of the a's here has to be replaced by one of these r's. Yeah? So in particular, if you put x equal to 1, then each of these a becomes an r, and you get basically this tells you how the right-hand side of the functional equation of the univariate function r of z looks like. So this is kind of the function reflecting the structure. And what we know already is for the function r of z and 1, it behaves as z tends to rho, and rho is, for instance, for the general tree, it's 1/8. For the other trees, it's other constants. We know that it behaves in such a way, in the constant minus other constant times this root term, which gives you the applicability of the transfer theorem. Okay, we remember this. And what we need is to get higher moments is the mth order derivative with respect to z evaluated at x equals 1. So this should be doable from this as well, but it looks scary if you look at this functional equation, but still we don't want to have an exact solution, just only asymptotics. So this is enough, just the asymptotic main term, and this can be done with it. If you look at this function we are interested in, then from the functional equation, one can kind of do a computation first, and it decomposes in 3 subterms, where each of these subterms looks like this. And the important thing is these are sums involving partial derivative with respect to x of our function of the bivariate function r. Yeah, this is the important thing here. And positive coefficients. So that means we are interested in this Rm, and this Rm of z is on the left-hand side. And on the right-hand side, if you solve for Rm, then you have the partial derivative. No, you have, yes, the partial derivative of the phi function with respect to the second variable, evaluated in z and r of z times Rm, plus some other part, Hm, which is more complicated. Okay, and now this Rm can be shown to be asymptotically equal of this nice shape. And you see that if we have that, then we can use a transfer theorem to get the asymptotics for the coefficient of it. So why that? Write Rm in this form from the previous equation where we solved for Rm, and then we can prove this by induction. Because note that if you do the nth order derivative and you are just looking for the asymptotic main contribution, okay, then this is Rm, and a second order term and further terms, which are not, turns out, not interesting for us. And when do we get a contribution that is significant? Well, whenever we have a smallest power of 1 minus z over rho in the function Hm. And when do we have a smallest power of this? Then we have to look at this scary looking big sums and double sums, which was called Gi of m, G1, G2, and G3. But the main contribution only comes when either you take from these partial derivatives, you have a lot of partial derivatives with respect to x, several higher order, and the orders were encoded in these Ri's, which were the summation indices. And if all of them, but exactly one, is equal to 0, then you get the most you can have, then the smallest power of this. So that means, and the differentiated terms, so one term is differentiated m times and all the others are not differentiated at all. And this one term contributes this part here, because this was all put to the left-hand side. So the contribution is just this here. Or exactly two terms are differentiated. So the sum of the orders of the differentiation sum up to m, and each of them contribute their main term. So this one, which is then strictly smaller than of order m here. So that means we can use the induction hypothesis on this, and also on this for the first case. And if we do that, then we get that Hm looks like, well, like some constant times this, and going back into the functional equation, we can even, well, we cannot exactly determine the constant immediately, but we can use the induction hypothesis on R to get some recurrence relation. So dm is built from the structural function or its second order derivative, which is this here. No, it's derivative with respect to a times some, let's say, the constants that are involved in this by the induction hypothesis. And we get such a recurrence with this constant b, and this is exactly the same as the function f we encountered already in the functional equation when we solved for s of z. But this is not a coincidence, because this is based on the same kind of computations, namely the derivative of such a double sum and then evaluating is basically the same type of computation, and that's why the same function here occurs again. Yes, and finally from this, when we know that Hm looks like this, we immediately can have that Rm is Hm divided by this quotient, which is under control because the function phi a is known. And well, why is it known? Because phi a is also the function that determines the singularity via the system tau is equal phi of rho tau. So tau is the value of R at the singularity rho. And both equations must be satisfied if we have a singularity at this point. And so therefore we can use that 1 minus phi a is just depends on this root in a root times a constant. So we can go with this into this equation and get the proposition here that Rm looks like this and Cm satisfies this recurrence equation here. And okay, and this recurrence equation looks very familiar to people who know the Airy distribution. Namely, if you scale it a little bit, so you crank out the factor mu, which is b divided by a times phi aa, then you take the normalized expectation. Normalized here, you have a mu and n to the 3/2, and the nth moment of this, then you get an expression where this Cm occurs, and these normalized moments satisfy this recurrence, and this is exactly the recurrence of the moments of the Airy distribution. So that means the nth moment behave like the moments of the Airy distributions, and moreover, the Airy distribution is uniquely determined by its moments. So that means this fact here gives the theorem that this normalized second index not only weakly converges to the Airy distribution, but also it converges with respect to all moments. So that means all the moments of this converge to the corresponding moments of the Airy distribution. Yeah. Okay. So I have only a few minutes left, so that means maybe I just summarize what we have got here. So the expectation of the second index is therefore proportional to mu times n to the 3/2 in average, where the mu is given by some constant, and we have computed the constants. Well, for S plus, I showed you was this constant here, 1.76. If you take S minus, of course, the computations are similar. You have to replace some k by some l in the functional equations, but that's essentially everything, and redo all the automatic computations and get for S minus, it has the same shape and with a different constant here for the general case, and it is also Airy distributed if you do the normalization like this, because this is the same type of computation. For simplex trees, no, for normal trees, we can do the same computations. Here we get only numerical results, not kind of explicit constants. Here for S plus, the constant, and for S minus. And for simplex trees, it's interesting because for S plus and S minus, you get the constant explicitly, and in both cases, the same constant. So that means in the main term, there is no difference in the expectation of the second index. It's only an asymptotic, of course. In the second order term, there is a difference because there we get these constants here, and there is a difference in the second order term. Yeah? It's of order n instead of n to the 3/2. But here the two second indices are very close to each other. So there's in the main term, we don't see a difference. Yes, and all these things could be done also in the unlabeled world. So here the computations are more complicated. You need cycle indices of whatever. I just refer to this. Here we have the same phenomenon. The figures are a bit different, of course, and nothing is explicit here. So just numerics for all the constants involved as expectable for these unlabeled cases. Yeah. Okay, but here we have explicit words. So I'm done with it. Thank you very much.
Sir, I have a question.
Some questions? Anybody?
Yes, sir. Yes, sir. I have.
Switch on the webcam on the microphone.
So do you have microphone on?
Can you ask a question?
There are a question, Cyril.
Yeah.
Question from Dr. Mohammed.
Yes, sir. My question is that what is the purpose of sacking index? And can we apply this index to any graph like you are using for tree graphs? Can we use it in any kind of graph like chemical structures? There are many kind of cycles. Can we use it there? And a second question is that how you have calculated these results? Have you used any kind of software by which you compute your final outcome?
Yes, the second index was introduced for the balance of phylogenetic trees, to kind of to look how you don't hear? No. To look how close a phylogenetic tree is to a balanced tree. For biologists, this was of course always interesting, because what we see in the evolution, the taxa that we see right now, all of them have evolved for the same amount of time. So therefore, it is kind of expectable that the phylogenetic tree behind is rather balanced. So therefore, they are interested in such balance indices. And as a gold tree is, let's say, not too far away of a phylogenetic tree or of a tree in general, it is expected that these two indices are still a kind of a measure of how balanced such a structure is. For a general graph, well, it depends how. First of all, you need a root, otherwise you cannot define the second index in the same way. I mean, if you want to use exactly this index, you need a root and distances from the root. And then probably also kind of a measure how far the graph is from a tree. And if it's, well, close enough to a tree, then kind of the second index might make sense to measure the balance, whatever that means then in the particular graph, in some, let's say, reasonable way. So far to the first question.
Yes,
the second question, yes, of course, I did not do all these computations by hand.
Yes, sir.
I used Maple as underlying software to help me with getting these explicit things, get these kind of fractions that appear here in a kind of normalized way. And of course, to do all these numerics, partially they are also rely on iterating functional equations to get accurate numerical results, which is using some 100 iterations, and it's to get
that's why you use Maple.
accurate results.
Okay. Thank you, respected professor. In fact, my work is also about the topological indices. I worked on Zagreb connection indices, modified Zagreb connection indices, multiplicative modified Zagreb connection indices. My research work is about chemical graphs. I also worked on work for computation of the topological indices, which tells us about the chemical reactivity, melting points, boiling points, and related to chemical reactivity. Thank you.
Zagreb index, you said, yes.
Yes.
Can you write in the chat the names of the indices that you mentioned?
For me?
Yes. Can you write the names that you mentioned in the chat so that it is clear for everybody?
In fact, I computed many kind of Zagreb indices. Basically, there are simple Zagreb indices. Simple Zagreb indices. Then there are further subdivisions in Zagreb connection indices. ZC1 star, ZC2 star, ZC3 star. Similarly, there are further modified Zagreb connection indices. I will share my ResearchGate link. There I published 6 research articles. All the research articles are published in international journals. I didn't pay any money. All the papers are published in subscription-based journals, and all the journals are sci journals. I just put my ResearchGate link in box. You can read further details. Thank you.
Okay. So further questions or comments?
What is your interpretation that for the simplex we have S plus equals to S minus?
At first order.
I didn't understand the question.
Do you have a quick explanation of why S plus and S minus have the same first asymptotic term for the
Yes.
simplex case?
Yes, because it seems that if you cannot go through many goals, because every goal, if you look for a path from a leaf to the root, then either the leaf is a child of a reticulation vertex, and then of course there you have to cross a goal where the two paths may be of very different lengths. But all the other cases are that the leaf you have to, if it's not the child of a reticulation vertex, then you cannot cross any goal, because whenever you reach a reticulation vertex, then the child must be a leaf, and therefore you cannot go on a path to some vertex where you are now, the next vertex is a reticulation vertex. So this is a very special case that you cross the goal. And so the typical case will be that you don't have to cross a goal at all on a path from the leaf to a root. And if there are no goals on your way, then of course S minus and S plus are the same for, well, or the heights H plus and H minus for this leaf are the same. And most leaves more or less contribute like this, the same to the two second indices. And therefore, this difference in the special leaves, which are just children of reticulation vertex, doesn't make up for enough differences between S plus and S minus that we see that in the main term.
Okay, thank you.
Okay, is there some other questions?
So,
yes.
Yeah, hi Bernhard. So happy to
hello.
Hello. Hi, nice to
see you.
meet you.
I mean, I
Very
don't
nice
see you right now.
presentations. Very good. Okay. So just one quick question. Do you see, Bernhard, it would be possible to calculate number of the paths between two, for example, between root and the leaves for this kind of the special, I mean, let's say biological
number
network?
of paths, I think yes, because there is work I did with some with Michael Fuchs and with some colleagues in Stanford, where we computed the number of goals.
Okay.
So I guess that should be possible. It's maybe, I mean, number of goals is something different, of course, but number of paths is from the computational difficulty, maybe similar to computing the height of a tree. No, not the height of a random node of a tree. And this is Maya and Moon, did it for trees. And I think it's a little bit more complex, of course, but yeah, I think that should be doable, yes.
Okay, perfect. I mean, from biologic point of view, it's very interesting for them to see number of a paths, because they consider all the nodes as a metabolism and all the age as a reactions, and they would like to see how many pathway, let's say, flags between the node, between the root to the leaves has, and try to count number of these paths that can be, understand how many paths there is for a special root and nodes, and count the number of the paths from the root to the leaves. So yeah, very good.
So Marefat, who did you say is interested into this or is doing this?
Sorry, I couldn't hear you good. Sorry.
Who is interested into this?
Actually, my postdoc supervisor, Jürgen Zangelini, told me that it's very interesting. He's a biological person, and yeah, Definitely, I will come very soon to the Bernhard to discuss a little bit more details about that. Yeah, so yeah, definitely I can give some more information about all the details. So yeah, but from biology perspective, it's really interesting this path because as far as we know how many paths there is some optimal paths between root and leaves, and they try to choose this one and to knock out another path or something like that, and they would like to know how many paths there is and how can they remove them or something like that. I mean, biologically there are very nice interpretations of them, and it's very useful for them for a special purpose, for especially for drug productions or something like that. It's very interesting.
I see, yeah. Okay, but we can, maybe you can pass by, you are in Vienna, so
yeah, sure. Definitely, I will come soon. Thank you very much. Thanks.
Okay, thank you. Any other question? No, so
As
yes, Mohammed again.
As the professor told that this type of work, this type of methodology has a great importance in biology. According to my opinion, this type of indices should be computed for the DNA network, backbone DNA network. I also worked on backbone DNA network by using Zagreb connection indices. And I don't know, this methodology could be helpful if I apply there, because the structure of the DNA is a cyclic structure. It's not a tree. That's why I'm unable to give any comment that I can apply this one or not.
So I invite you to send email to Bernard, because it is indeed the case that the methodology that he presented, some other parts that he did not presented, could perhaps send them cycles. So you should send to him the exact model, and I think he will be happy to have a look at it. And I will try a question also. So you consider nodes who could have two parents. But what about if we have three parents? So there will be a simple tree like this and a simple tree like this. Oh, people were not seeing my head. I should sure the way
I understand your question.
the tree like this, but we could have a tree like this.
I mean, well, I think the one has to think what kind of substructures one, because for the phylogenetic network, you just have these reticulation vertices with two incomes and one output. If you allow, let's say, also three in, one out vertices, then the question arises first, what kind of structures can appear in that way, and what does then, let's say, concepts like tree child, normal, simplex, and so on, which are the reasonable concepts there? And then I think it's certainly possible to tackle this in some way.
Thank you.
It's but you have to restrict to some subclass, like here. We only consider tree child networks, and here gold trees, which are rather special in this kind of zoo of phylogenetic networks. For phylogenetic networks, this is maybe not interesting. I don't know. I'm not an expert in evolution, but I did not. I did not hear even from bacterial evolution that they have more than two species merging into one. But yeah,
I think that you could have this.
I don't know.
Genes of different groups of.
But I think the methods will also work in some special settings.
Yes, because my intuition is that there is something which is universal behind, which is that you will still have Airy distribution, even if you have more guide like this. Parameters on the trees.
I think it's always the kind of how tree-like this structure is. Like here in gold trees, where you allow that you don't have too many let's say, interwoven goals, then of course it gets super messy. Already level 2 networks where you allow that every bi-connected component has 2 reticulation vertices, or one, or as both is allowed. Already here, it is very complicated just to count the networks, because this is done with so-called generators. And for gold trees, you have basically one generator, namely this kind of goal, and everything else is tree-like. And in, I think for level 2 networks, it's 64 generators or something like that, so much more. So that can be very messy very quickly. And if you have even 3 incoming edges, then you need to restrict to something. And it depends how tree-like it stays, if you get airy again or not, I would expect.
Okay, so is there any more comments, questions?
There is a question on the chat, Cyril, from Suhail. Last chat, last one.
It was more a comment than a question, I think.
There is this methodology apply cyclic trees. I'm right. The question of
so what Bernhard presented was with cycles, but there is an extension of it which could allow to handle cycles, enumeration and asymptotics. But to be sure of what is exactly doable, we need a more precise definition of what will be the structure that those people will be interested in. And I invite them to send email to Bernhard, like this. Bernhard check if indeed it's possible to handle them or not. So I think that it is answering to all the questions. So let me comment that I think that the next seminar will be on January 7, and the speaker will be Shen-Hui Wang from Taiwan. So thanks everybody. Bye.
Thank you. Thank you for this nice talk. Thank you, Bernhard. Thank you, Cyril. Have good holidays and Happy New Year 2025. See you in January. Thank you.